time to start. It is my great pleasure to introduce Raquel Diaz.
Okay,
she will continue sharing with us some results about torsion patterns in Covano homology.
There's
Thank you for being here. Let me click
on.
record.
Okay, I think that deals with it. I'm sorry about that, but I think we should be good. Okay, so Jose Carlos, you're up.
Very fine. Thank you very much, Colin. It is my pleasure and honor to be part of this Lou Kaufman 80th birthday and celebration. I would like to start saying a few words about the influence of Lou in Mexico. As you know, Lou, he has had a lot of influence in many countries and, of course, many persons, but maybe it's not very well known, the mathematical influence in Mexico. So I will mention just 2 or 3 activities that he has had in Mexico in order that you know this influence here in my country. About 30 years ago, I don't even remember exactly how many, Lou was invited to come to CIMAT in the city of Guanajuato, the main campus of our research center, and he gave us a very beautiful and nice course at that time. More recently, in 2019, as part of the GeoTop seminar, GeoTop A seminar, this is our website, he gave us a marvelous talk with this title, Unitary Braiding and Topological Quantum Computing. And let me just say that you can find the video of this talk in our website. And secondly, that it has had almost 4,000 views since 2019. And more recently, about a year ago, January 11, last year, he gave us a tremendous talk in our first presential GeoTop conference in the city of Mérida here in Mexico, with this title, Reconnection Numbers of Knotted Vortices, that you can find also this talk in YouTube. Okay, so thank you very much, Lou, for this work that you have done here in Mexico. And certainly I can tell you happy birthday. And as we say in Spanish, tenga usted muchos años más por delante. What I mean is, hope that you have very many years in your life from now. Okay, so let me start with this talk. I'll be talking about essentially 2 topics. One, we call it two stratifiers, and the second is just a proposal, a very naive proposal to use polynomials for studying 3 manifolds. The first part of the talk is with our we've been collaborating with González Acuña and Wolfgang Heil in the last 30 years or so about the topic of two stratifiers. The last part about polynomials is a joint work with the young researchers here in Mexico, José Ángel Frías, Fabiola Manjarres, and José Luis León. So I'll be talking for a couple of minutes about what we call 25 years ago or something like that. We call it the Tri-genus of 3 manifolds. You know, at that time, we were studying the problem of Luster's-Niemann category of low-dimensional topology, in low-dimensional topology, concretely, the Luster's-Niemann category of 3 manifolds. And then at that time, we found from papers by Sinkoff and Takens that, I mean, you could have, for any 3 manifold orientable or non-orientable, the composition in three handle bodies, whose interiors are disjoint. I mean, just said this very briefly, these are three orientable handle bodies that they glue it along the boundary in a nice way. That's all what I want to say with this. And of course, you will tell me for the orientable case, yes, B1 is a ball, and B2 and B3 is just essentially the Higger splitting. Yes, but for non-orientable manifolds, this Tri-genus has a little bit more sense. Why I mention these Tri-genus now? Because two reasons. The first one is that the space E that I call here the union of the boundary, the intersection of the boundaries, meaning what in my picture is these three lines, is going to be exactly what I mean by a two-stratiform. And I will say this L is this point in my picture. It's just the intersection of the three boundaries. It's going to be a link in the manifold, I mean in M, or it's going to be a link in what is going to be the stratiform that is E. Okay, so why I mentioned this? Because it was the first time that I remember that we met with these two stratiform spaces. Okay, this is not the point, but I just want to mention that for Tri-genus, I'm not going to say too much about this, but I want to mention just one result. For non-orientable three manifolds, of course, we found that the big one is, I mean, if you define the Tri-genus first, meaning if GI denotes the genus of the boundary of BI, and you order this genus G1 less than equal to G2 less than equal to G3, then you define the Tri-genus of M like the minimal triple G1, G2, G3 order lexicographically. And what we found is that this genus, this Tri-genus can be zero. I mean, the big one is a ball, or the big one is a solitary. And let me just say it briefly without an intention to say more about this Tri-genus, is that we could find in terms of algebraic topology when is zero, I mean this Tri-genus, and when is one, and this is in terms of, I would say, algebraic topology, in terms of the Stiefel-Widner class and in terms of the box thing. Don't want to mention too much about that, because I want to mention you the second reason why I'm mentioning Tri-genus. The second reason why I'm mentioning Tri-genus is because you can see here two papers that were published related to that in 1999. And you can notice that in these two papers, Victor Núñez was one of the authors. I just want to remember Victor Núñez in this occasion, because unfortunately, Victor, our colleague and good friend of many years, he passed away last year. And I just want to remember Victor in this occasion related with this Tri-genus. Okay, so now that we have found this two-stratiform in our previous work, you know what happened in about 10 years ago is that we were beginning to learn a little bit about topological data analysis. And we learned at that time that the typical spaces models that appear in this topological data analysis were graphs or were surfaces. And then we thought at that time that for applications, it would be good to have the next level of complexity in models. And then we choose that the next step or in complexity for this, for studying these spaces were exactly the two stratifies. Why I mean, because why we choose this one? You think very fast. What happened is that two stratifies are going to be the equivalent to graphs without endpoints, but in 2 dimensions. And secondly, because we hope that the two stratifies were computable. I mean, they were good for application. So we started studying these spaces by themselves. Okay, so what is the two stratifies? I will say it just very briefly. It's just, for us, a two stratified is a connected finite dimensional simplicial complex where regular neighborhoods of points are like this picture, meaning the regular neighborhoods are, if this is P, are just a union of the semidisks attached to this line, to this red line. I don't allow the equal 1 because I don't want two stratified with boundary, okay? And this is a way to say it very, very briefly, what is. Another way to say it is just that two stratified is just a space where outside a collection, outside a link is just a collection of surfaces, and that would be a very, very short way to say it. What is a two stratified for us? I could say it more carefully, but I don't have the time to do it. But let me just tell you that the last 10 years or something, we've been studying these two stratifies. Of course, at the beginning, we were very optimistic, and we thought that we could find a classification and invariance and so on. But, you know, it turns out that the problem was a little bit more difficult than we thought. And then what we did in the last few years is just to study a few things about the stratifies. And then, first of all, I'm going to mention 2 or 3 what I call theoretical results about the stratifies. And then I will mention two or three that I think they are close to applications. Well, first of all, we could prove that two stratified groups are solvable word problem. And also we did at that time this natural question: which closed tree manifolds have spines that are two stratifies? And the answer that we could find, we were lucky to find that then N is a very, I mean, the kind of manifold that you can find with this spine is just a connected sum of length spaces, S2 bundles over S1, or and RP and possible RP2 cross S1. Also, we started, thinking in terms of homotopy, classification from the point of view of an homotopy. And then we found, for instance, if the fundamental group of the two stratified is trivial, then we found that then E is a wedge of S2s, or more recently, with the work essentially of Alejandra Negrete, we found that the fundamental group is free, then the stratified is homotopically equivalent to a wedge of S1s and S2. Let me just say because we were before interested in Lucer-Sneerman things, that with the result, you can calculate completely the Lucer-Sneerman category of two stratifies. And I won't say more about that. Okay. Now, I will mention a couple of things that we know about two stratifies that maybe they are closer to applications. First, we describe a method for counting the number of one connected trivalent two stratifies with a given number of singular curves and two manifold components. When I say trivalent three manifolds, I mean that D is equals to 2 or D is equals to 3. That's what I mean by a trivalent stratified. And the singular curves are are precisely the set of points where D is equal to 3. That's the singular curves that I'm talking about in this theorem. And then we found that also an homology classification of trivalent simply connected in terms of homology. So we proved that the trivalent two-stratifold is simply connected if and only if the first homology group with coefficient C2 is 0, and simultaneously H1 of the stratifold with coefficient C3 is equal to 0. And I could mention more results, about the stratifolds. In fact, fortunately, recently we already wrote a survey about our results of what we know about the stratifolds that I will mention in a minute. Also, I'd like to mention this result by Miriam Hernandez-Quechul and Jesus Rodriguez-Biorato related to stratifolds. And I think this is very much close to applications. Like we do in knot theory, that we find classifications of knots with few numbers of crossings, when we start the classifications of knots, that's what they do. Miriam and Jesus, they have a Python program that computes and prints all distinct trivalent simply connected to stratifold graphs up to a chosen number of white vertices. And they describe what they do in this abstract. But of course, here you will say, what do you mean by a two-stratifold graph? Because you've been talking about just two stratifolds. Yes, is a tool that we use systematically when we study the stratifold, that we associate to a stratifold a graph. And this graph is precisely what I call here the two-stratifold graph. And what is this graph? It's very simple. For each singular curve, I'm talking about trivalent stratifolds. For each singular curve, for each element of the link, you add to the graph a black vertex, and for each surface that you obtain after deleting these singular curves, you put a white vertex. So that's what I mean. And then, of course, what are the edges? The edges is the way at the boundary of the surfaces attach to the singular curves, I would say that. So in other words, we associate to a two-stratifold graph, and this is very convenient for studying two-stratifold. In fact, if we want, we can essentially study two-stratifolds in terms of graph. I would say with weighted graph. Not just graphs, weighted graphs. And you could study two-stratifolds just in terms of weighted graphs if you wanted. We haven't done that. Okay, so this is a result that I wanted to mention to you. And this is the more or less some references that I will give you about this topic. The first one is the one that I told you that we wrote a survey recently about this topic, about two-stratifolds. This is the paper by Miriam and Jesus that I already mentioned to you. This last reference I mentioned to you because I wanted to emphasize that Makoto Osawa and Matsuzaki, they have studied the spaces that they call it. They call them multi-branch surfaces. What is a multi-branch surface? Surface is nothing else like similar to our definition, but they allow they equal to 1. So that's I think very briefly what is a multi-branch surface. But let me say that they study these multi-branch surfaces not from the point of view of understanding two-stratifold by themselves, but they study multi-branch surfaces, trying to apply the multi-branch surfaces to the study of 3 manifolds. Okay. So why I mentioned reference number 5 and reference number 6? Because it turns out that we already found some examples where these two stratifies appear in applications. In the reference number 5, they were studying the energy landscape of the cyclooctane. And what they obtained is that the energy landscape of the cyclooctane, it turns out that it's a two-stratified. And in terms of topology, is exactly this. They found that this energy landscape is just a two-sphere, and then a Klein bottle with these red curved intersections. That's what they found in these papers published a few years ago in this energy landscape of the cyclooctane. Notice that this is a two-stratified, in fact, it's a four-valent, meaning D is equal to 4 or D is equal to 2. The second example that the other reference that I'm mentioning here, reference number 6, excuse me, is a paper or is a work by Atsiri Gonzalez, a Mexican young researcher, that he is working together with, with people working in physics, and they study the three-dimensional orbits in a convective flow. This is a paper just recently finished, and what they found is that the model that they found, by the way, using topological data analysis, is precisely this. And what is this picture? Is just a two-dimensional torus where you attach this band. Okay, this is a band. This is a two-dimensional torus. These are two red circles, and then you attach this band to this torus along the red lines, and then you obtain the model that they found in this reference number 6. So that's why I mentioned this that this kind of model already appeared in some applications. Okay, so there is a way of, I could explain how we went from studying two stratifiers to now to propose, I insist, maybe a very naive way to introduce polynomials to the study of three manifolds. But I could talk about why we came from one topic to the next topic. But I don't have time to do it. So let me go to the point. First of all, I have to talk a little bit about graphing surfaces. So first of all, I have to give, so I'm going to talk about graphing surfaces. So I will say that a graph in a surface F, I will say that a graph G is cellularly embedded if the complement of the graph in the surface is just a collection of disks. In other words, each component of the complement is homeomorphic to a disk. That's what means that the graph is cellularly embedded. Another definition that you can find in the literature related to graphing surfaces is this one. Two graphs, one G containing F and G dash containing F dash, are equivalent if there is an homeomorphism from F to F dash, such that the image of G is G dash, meaning the embedding is the same. But apart from that the homeomorphism restricted to the graph G to G dash should be a isomorphism of abstract graphs. So that's what I mean by two graphs equivalent in a surface. Okay, so given these two definitions, let me say that in the literature about graphing surfaces, they introduce several polynomials of these graphs. I will mention just two, the typical polynomials that they talk about in the literature related with graphing surfaces. I will mention the famous Tute polynomial defined for any graph. I mean, not necessarily taking in account the surface, not yet. And this is just the classical Tute polynomial defined in this way, and where the ingredients in this formula are the edges, the vertices, and the number of components of the graph. The other polynomial that I want to mention is what is called the ribbon graph polynomial. Here I have to say something. This polynomial is not exactly defined to graphs in surfaces. They are defined in ribbon graphs. What is a ribbon graph? Just take the graph, let's say take the graph G, and consider a regular neighborhood of this graph in the surface. And that's what I call a ribbon graph embedded in a closed surface, okay? This polynomial is defined for ribbon graphs, not exactly for graphs. And the polynomial is in 4 variables, is defined in this way and with this formula. And you can notice that the ingredients are the edges, the vertices again, the number of boundary components of G, because remember that G by now is a surface with boundary, the number of connected components of G, and the others numbers R and N are just combination of the others. This last number, in our case, is going to be always 0, because I will also always consider orientable surfaces. Sorry about my coffee. Note that in this definition, in the previous formulations, the polynomials consider all the subgraphs A's contained in the graph G, such a way that they have this property. So that's why you have here many summands. You consider one summand for each graph A with this property. Okay, I could talk to you also about the Penrose polynomial that I learned yesterday, that there is something called the Penrose-Kaufman polynomial, that I was not aware of this Penrose-Kaufman polynomial till yesterday, but I'm sure that all what I'm saying, it could be good also for what is called the Penrose-Kaufman polynomial. Okay, let me say that in what I'm going to say, Jose Frias, he has developed a software for computing these graph polynomials for the Tute polynomial, for the Penrose polynomial, or for the ribbon graph polynomial. He has a software, and that's the software that we are using for calculating these ribbon graph polynomials. Okay, let's come to the point, meaning, suppose that I'm talking about now 3 manifolds, okay? So how we want to think about polynomials in 3 manifolds. Let's consider let D as AB be a 3-manifold Hilbert diagram of genus G greater than or equal to 1. By that I mean that S is the Hilbert surface, A and B are the boundaries in S, in the Hilbert surface, of 2 systems of the composing disks for the 2 handle bodies in the Hilbert splitting. Let us call gamma the union of the 2 families, A union B, contained in the Hilbert surface, and let call gamma the Hilbert graph associated to D, to the diagram, to the Hilbert. I'm sorry, to the Hilbert diagram. Okay. And why I mentioning this like a graph, because the vertices are going to be just the intersection of the 2 families, and gamma is going to be, the edges of gamma is going to be the complement of these vertices in gamma. That's what is the edges. So for instance, this is the classical Hilbert diagram of a Poincare homology sphere. that you can find in the classical book by Hempel. And then you find here two families. The black family is, let's say, the A family. There are two curves, and the two red curves are the family B. And so my graph, gamma, it turns out that it's just the union of that. I mean, the union of the reds and the blacks, and the intersection that in this case 13 vertices. And this is an example of what I mean by gamma and so on in a Higgs diagram. Okay, so first step. Now, let's suppose M is a closed orientable three-manifold S. Let M is a closed orientable three-manifold and S be a surface of genus equal to the genus of them, meaning I consider the surface with the genus of them. Okay, so first step. Second, let H be the family of all Higgs graphs of M in S, all the, I mean, in other words, you consider all the Higgs diagrams in S of the manifold M, and then you consider, and then therefore you can consider from this Higgs diagram, you consider the Higgs graphs. And then consider the subfamily of this H be the ones with minimal number of vertices, So we have three claims. First, for this, with these G's and M's, what I have just defined, I would say that if M is irreducible, then S minus gamma is a finite number of open Ds for each gamma and G, meaning the embedding is cellularly embedded. Gamma is cellularly embedded. This would be our first claim with this hypothesis. Remember, it has minimal genus and is the minimal number of intersections possible in the Higgs graphs. Okay, and this claim is just, this is a standard, meaning if two graphs are equivalent, the polynomials are the same. This is just comes from directly from the definitions of Penrose, Tutte, or any ribbon polynomial. So if two graphs are equivalent, the polynomials are the same. And finally, that's our final claim. If N and G as before, remember, as before, then the number of gammas in G, the number of gammas, the number of graphs is finite up to equivalent class. Okay, if you believe that, then we have a possible way to define polynomials. As a consequence, for each graph polynomial P that you choose, we have a finite family of polynomials. Using this family, we may then find a polynomial invariance for three manifolds. Yes, I agree. You will tell me that's impossible to calculate, okay? Yes, I completely agree. Even if everything is fine in our definitions, but it turns out that we did two things. First, yes, we can make it, we can calculate this polynomial for length spaces. Of course, you will say that's too easy. Okay, but yes, you can do it. Why you can do it? Because using the classical Brody theorem that you have in front of you, using that, you can prove essentially that for each LPQ, for each length space, you have just one element in the family G. I mean, in the family of Higgs graphs, you just have one. That's what happened for length spaces. By the way, this result, even so, we have a proof of that. I heard that González Acuña and even Vinicio Gómez, they have a proof of this, of what I'm saying now. If I am wrong, it's my fault. No González Acuña or Vinicio error, okay? But I believe they have also a proof of that. As a consequence, you know, we can find the polynomial of length spaces. And yes, we can do it. I won't say that. Using Jose Frias software, then you can calculate for a few examples of length spaces. For instance, the Tute polynomial, the Penrose polynomial, or even the Penrose, the ribbon graph polynomial. And you can check here what it should happen. For instance, if you calculate the polynomial of phi 2 and the polynomial of phi 3, then it turns out that as it should, they should be the same. Okay, so that's what I can say you about let's say what we have done. I mean, it's possible to do it. Also, I think it's easy to see. I have just a couple of minutes left, but I think it's more or less easy to see that using this polynomial, you can, from the polynomial, you can extract P. That means that certainly you can find the fundamental group. I mean, using the polynomial, you can find the fundamental group of the length space. Okay? We believe, but we have not done it, that this polynomial is a complete invariant, meaning that the polynomials, we don't know exactly which one, the Penrose, the ribbon polynomial. You can also extract Q, and therefore we believe that this polynomial should be a complete invariant for length spaces, but I insist, all what we can find is just P. Okay. The second thing that we can say about these polynomials is what I am going to say. Yes, for manifolds with genus 2, let's say, like for instance the Higger diagram. I mean the Poincaré homology sphere, like here you have a diagram. We can calculate using the software the polynomial of this diagram. Yes, we can calculate. In fact, by the way, this embedding is cellular. It's cellular embedded, this graph here. And then you can calculate, certainly, you can calculate the polynomial for that diagram, okay? And then, in fact, you can see here, this is the ribbon polynomial, or the ribbon graph polynomial for the Poincaré homology sphere. Is all this, you can do it. Yes. Of course, you will tell me, okay, but you are just finding the Higger polynomial. I'm sorry, the polynomial of one diagram. That's correct. Even in one concrete example, like the homology sphere, the homology Poincaré sphere, we cannot say that if the minimal number of vertices is 13 pairs, and we know that the genus is 2, but we don't know if the number of graphs in G is just 1 or more. So even for calculating the polynomial for something like the homology Poincaré sphere, we are far from that. But we can just propose the following. You know, we or somebody else that they have good computer power, you know, and they could start finding the calculation of many polynomials of Higger diagrams, very many, you know? Meaning you create a cloud of points using these polynomials. And then you can apply just to the Higger diagrams of manifolds. And then you can apply some data analysis techniques like topological data analysis or whatever. And then you could dream from this analysis to try to understand something about the three manifolds? For instance, can you detect, using the polynomials, using that analysis, that the manifolds, they have trivial fundamental group or not? For instance, can we dream doing that? Okay, so that's the only two things that we have done. First, we can calculate the polynomial for length spaces, and secondly, we can propose to study three manifold studying these polynomial for Hilbert diagrams. That's it. Okay, so here you will find three references. The last reference, number 10, as you can see, is the reference where you can find all the literature related with graph on surfaces and polynomials. We are not experts at all in graphing surfaces and nothing else. We just, when we learn about these graphing surfaces and polynomials, we've been trying to introduce these polynomial for graphs in surfaces for the study of three manifolds. And with this, I have to say many thanks for your attention. And I have to say thank you very much from CIMAT in Campus Mérida in Mexico. Thank you.
Thank you. That's great. I'm going to turn off our recording here.